All right, so for this video, I'm going to go through and just look at a couple of the questions at the end of the chapter 4 material in the online textbook. And then with this, I also sent the slides themselves out through the announcement in Canvas. So if you just want to look at those and work through them yourself, you can, or with the video, I'll just give them a little bit more information as I kind of talk about how to work through them. So if you want a chance to work through them on your own, just pause the video because I'm essentially just going to show the answer just so I'm not sitting here doing nothing. But with the first question here, we're given a handful of substances, their chemical formula. We want to determine the oxidation state for each of the elements in these compounds. So remember, with the oxidation states, sometimes called the oxidation numbers, we have different rules to assign these. So with metals, group 1, group 2, aluminum, those are always going to be +1, +2, or +3, respectively. So kind of the same thing we were looking at when we were looking at the ionic charges in ionic compounds. Because with these ions, the oxidation number is going to be the same thing as the charge. It's just with the covalent substances, there's a little bit of a difference there. So when we are looking at the nonmetals, we can always say fluorine is going to be -1 in a compound because it's going to be the most electronegative element. Oxygen will pretty much always be -2, except for when it's with fluorine for the same reason. But we'll see with the superoxide example here, there is a couple of exceptions. And then the halogens also typically going to be -1 in a compound, except for if we have them with oxygen or fluorine. And then the other nonmetals, if we've got them with something like oxygen or fluorine, we've got to do a little bit of math to kind of figure out what that oxidation state is going to be. And remember, the sum of these oxidation states has to equal whatever the charge is on that substance. So if it's a neutral compound like we see with all of these, the sum of the oxidation numbers have to add up to 0. If it's the polyatomic ion, then the sum of the oxidation numbers has to add up to whatever that charge is. And the same thing if it's just a monatomic ion, then it would just be whatever that charge is. So if we just had a net fluoride ion with a -1 charge, the oxidation state would just be -1. But with all of these, we've got the answers here. So with most of these, we can actually just kind of assume what the oxidation number is going to be based on the position on the periodic table. So again, things like sodium, lithium, rubidium, always going to be +1 in a compound. Magnesium, always going to be +2. And when we're looking at the nonmetal, things like iodine or chlorine, pretty much always going to be -1, except for a couple of those exceptions we just mentioned. But even if we didn't recognize what those were, we could think about having to balance out that +1 sodium. So iodine has to be -1. In the case of element GD, we have to kind of actually figure what that is because we don't have a set rule for that element. But since we've got 3 of those chlorines, -1, the GD has to be +3 to balance it out. And I don't actually even know what element GD is. With the next one, lithium, again, always going to be +1. Oxygen, pretty much always going to be -2 in a compound. So if we've got 3 of those oxygens, that's a -6 plus the 1 lithium, so -5. So we would need the nitrogen to be a +5 to balance that out. Hydrogen selenide, so hydrogen with the nonmetal, always going to be +1. So if we've got 2 of those +1 hydrogens, we need the selenium to be -2. And that also makes sense based on the position of selenium in the periodic table. It's a group 16 chalcogen. The example in E, magnesium silicide. Magnesium group 2, always going to be +2 in a compound. So if we've got 2 of those magnesiums, it's a +4 overall. So the silicon needs to be -4 to balance it out. And then like I mentioned with the next one, that's superoxide. That's going to be one of the examples where oxygen's a little bit weird. So when we have oxygen with fluorine, it'll be positive. When we've got oxygen in a peroxide, it'll be -1. But when we've got it in a superoxide, it'll be -1/2. And that also makes sense because the rubidium's only ever going to be +1 in a compound. So if we've got 2 of those oxygens, they each need to be -1 to balance it out. And then the final one, hydrogen fluoride or hydrofluoric acid, depending on the state we have it in. But either way, that hydrogen's with a nonmetal, so it'll be +1. That fluoride always going to be -1 in a compound since it's the most electronegative element. So with a lot of these, we can kind of just based on the position of the periodic table, determine what they are. But with the examples in B and C, we do need to look at nitrogen and GD and kind of see what does it have to be to balance out everything else we have there. With the next one here, we've got a handful of redox reactions. And similar to the previous one, we want to identify the oxidation states for all of these elements so we can identify what's changing from the left to the right. So we can identify what's being oxidized, so what's having its oxidation number increase, as well as what's being reduced, having its oxidation number decrease. And then in addition to that, we want to identify the oxidizing and reducing agents. And those are kind of a little bit backwards because the thing that gets oxidized causes reduction. So that would be the reducing agent. And the thing that gets reduced, you can think about it, causes the other substance to get oxidized. So that would be the oxidizing agent here. But again, if you want to work through this on your own, pause the video because I'm just going to click through and look at the answers. But with the first one here, we've got magnesium as a pure element, so it's always going to have an oxidation number of 0. Same thing with the nickel on the product side. So when we're looking at those two elements in the compounds, we've got them with 2 chlorides. Each of them going to be -1, so the magnesium chloride has to be +2, and that's always going to be the charge of it in a compound. And then nickel can have a couple different oxidation states, but if it's also with 2 chlorides, it'll have to be +2 there. So since we're seeing the magnesium go from 0 up to +2, it's being oxidized. Since we're seeing the nickel go from +2 down to 0, that's our reduction half. And then again, with the oxidizing and reducing agents, it's kind of backwards. So with the magnesium, it's getting oxidized, so we're actually considering that the reducing agent. And then the nickel is being reduced, so we're considering that the oxidizing agent. But since nickel is part of nickel 2 chloride, that whole thing would be considered the oxidizing agent rather than just specifically the nickel. The next one here, we've got, again, chlorine, pure element, so it's going to be an oxidation number of 0. Even though it's diatomic, it's still just the elemental form. So when we look at the reactant, phosphorus trichloride, 3 of these chlorines is going to have an oxidation number of -1. So phosphorus has to be +3. But then in the product, now it has to balance out 5 of those chlorines. So we see the phosphorus get oxidized from 3 up to +5. And then the chlorine, specifically just the chlorine in the elemental form, so not the chlorine that are already bonded to phosphorus, but just the Cl2. This is going to get reduced from 0 down to -1 like these other chlorines already were. So we're having 2 of these chlorides, or 2 of these chlorines, excuse me, be reduced here. And then again, just looking at the oxidizing agent, just see the reverse piece there. But again, since phosphorus is part of PCl3, that whole thing would be the reducing agent. The next one is an example of a combustion reaction. So we're burning, this would be ethene. But when we're looking at the combustion reactions, we're always going to see oxygens reduced because it's always going to go from an oxidation number of 0, kind of like the chlorine above here, down to a oxidation number of -2 in carbon dioxide or -2 in water. And I'm going to change this thing. Hopefully the mouse was showing up. Yeah, hopefully the mouse was showing up before, but just so you can definitely see it now. So oxygen always going from 0 down to -2. And then we'll see the carbon's always going to be oxidized. Depending exactly what substance carbon's in to begin with is going to determine its initial oxidation number. So in this case, it'll be -2 because 2 of these carbons have to balance out a +4 from all of these hydrogens. But then it'll always go to +4 when it's going to carbon dioxide here. So in this case, -2 up to +4. The next one, zinc, pure element, going into a compound where it'll always be +2, so that'll be our oxidation piece. Hydrogen kind of doing the reverse, but it's going from +1 down to 0. So that's our reduction piece. And then again, since hydrogen's being reduced, it's part of the oxidizing agent, sulfuric acid, and then zinc would be our reducing agent there. And then the final one's a little bit weird, so I'll focus on the sulfur part second. But iodine, elemental forms of 0 down to -1, that's reduction. So it's our oxidizing agent. And then with the sulfur, this one's a little bit unique because with the reactant here, neutral compound, so everything has to balance to 0. So we've got 2 of these potassiums that are each +1. So it's a +2. Then we've got a -6 from all of these oxygens combined. So +2 - 6 gives us +4. or -4, excuse me. So the sulfur, both of those sulfurs have to balance out that -4. So they each have to be +2 to start. And then in the product, we see kind of a similar thing. 2 potassiums, each going to be +1, so that's a +2 overall. Each of these oxygens are -2, excuse me, but we've got 6 of them. So that's a -12. So -12 plus 2 gives us a -10. So if we have to have 4 sulfurs balance out a -10, they have to average a +2.5 here. But this one's actually a little bit unique because actually what happens is 2 of them go down to 0, and then 2 of them go up to +5. So it's a little bit weird there. But if we're just looking at the average oxidation state, which is what we're kind of focused on, it's 2.5. So it's kind of similar almost to the superperoxide from the previous one that was just 0.5. All right. And then with these next two, we've got an example of a acid-base reaction in the first one and a precipitation reaction in the second. And what we want to do is determine the products of the chemical equation, and then using that chemical equation, balance it, get the total ionic equation, and then get the net ionic equation. So that we're showing with the total ionic equation the true form of all of these substances. So we'll dissociate the aqueous solutions that stay dissociated. And then with the net ionic equation, we're only just showing the substances that are actually changing. So we remove those spectator ions. So with the first one here, acid-base reaction, so we're going to produce salt water. Because our base is calcium hydroxide, our salt is acetic acid. That means our salt is going to be calcium acetate. And then again, of course, water. So the calcium acetate, you would need a solubility table, but we would see this is fairly soluble in water, so that'll also stay as AQ. But the water itself, of course, going to be a liquid, so we're going to have L there. And then when we look at the reaction, if we were trying to determine the product, I should say, make sure you're paying attention to the charge. So this is our acetate polyatomic ion, C2H3O2. But if it only had one hydrogen to balance out, that means it has a -1 charge. But calcium's always got +2 in a compound. So if we've got calcium +2, acetate -1, we need 2 of these acetate ions. And then when we look at our equation, we now need to balance it because now we've got 2 of these acetates on the right, only a single on the left. So we're going to put a 2 in front of the acetic acid, and then we'll also need a 2 in front of the water on the product side. But now this is our complete balanced chemical equation. So we can take this and go to the total ionic equation, so dissociate those aqueous solutions, and then the net ionic equation where we then remove the spectator ions. So with the total ionic equation, all of these aqueous solutions are going to dissociate. So when we look at calcium hydroxide, it gives us that one calcium ion, +2 charge, but it also now gives us 2 of these hydroxides, and each of those are -1. So when we look at it, we're still conserving mass, conserving charge. We've still got the same amount of stuff. We're just showing how it truly is in this solution. Because once we dissolve it, it doesn't stay as the calcium and those hydroxide ions attached anymore. They break apart and then get surrounded by water molecules. And then the same thing with the acetic acid, going to break apart into that hydrogen ion and the acetate ion. But now that we've got a coefficient of 2 in front of that, we get 2 of each of those pieces, 2 of each of those ions. And then on the product side, we'll break apart the calcium acetate in a similar way. So calcium with a 2+, 2 of these acetate ions that are each -1. And then anything that's a pure solid, liquid, or gas, so anything that's not a electrolyte, like we'll see here, so the solutions that dissociate. But anything that's a pure liquid, pure solid, pure gas, we're just going to keep that formula exactly the same. So we don't have to change anything about the liquid water. We'll just keep 2H2O in our total ionic equation. So now when we look at this, we can see 2OH- 2H+. That's what's forming our 2 water molecules here. But now we've got calcium ions, we've got acetate ions, and then we have the same thing on the right-hand side. So with the total ionic equation, we're just going to remove these spectator ions. We're going to remove these ions that don't change from the reactants to the product side. So our net ionic equation, would just be focused on that hydroxide ion and the hydrogen ion forming the water molecule. But then we still want to keep the coefficients we have there. So that's why we've got 2 hydroxides, 2H+, giving us 2 of the water molecules. So now with the next one, we're going to see this is a precipitation reaction. So whereas the acid-base reactions give us salt water, so water is going to be typically kind of the thing we're focused on there in terms of these net ionic equations. What we'll see with this next one is we're going to get a precipitation reaction. So we're going to have two aqueous solutions that actually form a solid. And in order to identify what the solid would be, you would need a solubility table. So that would be provided for you. You have to just have to know how to use it like we've done in class, like you did on the other problem set. But with this reaction, it's going to be a precipitation reaction. So that's an example of a double replacement. So what we're going to see is the hydrogen and the chlorine are going to essentially team up because that's the positive from one molecule, the negative from the other. And then the calcium and the phosphate are going to do the same thing. So again, with the double replacement reactions, we just essentially have those ions switching place. So the positive piece from those two substances just swap what they're associated with. So when we look at our products, we're going to have calcium phosphate and hydrogen chloride or hydrochloric acid. But again, we want to pay attention to the charges. So chloride -1, hydrogen +1. So we can just have HCl. And that's a strong acid, so that'll stay dissolved, that'll stay aqueous. But with the other piece here, calcium +2, phosphate -3. So we get the formula here for calcium phosphate, and that's going to be pretty poorly soluble. So you might get a little bit of it to dissolve, but most of it's going to stay undissolved. So we're going to see a pretty good amount of precipitate form of this reaction. But now looking at it, we've got 1 calcium versus 3, we've got 1 phosphate versus 2, 1 hydrogen, 1 chloride versus multiple on the left-hand side. So when we go to balance this one, there's no certain order that you need to do it. But what I would do is focus on this phosphate. So we've got 2 of them here. So we need a 2 in front of the phosphoric acid. That gives us 6 hydrogens. So we need a 6 in front of HCl. And then we have to get a 3 in front of calcium chloride to balance out these 3 calciums, balance out these 6 chlorines. But kind of similar to the previous one, we can now take the pure solid, pure liquid, pure gas, and just keep that formula the same. But all of the aqueous solutions that are going to dissociate, we're going to actually separate those into the individual ions. So with the hydrogen or the phosphoric acid, for each of these molecules, we get 3 H+ ions. But we've got 2 of these molecules. So we get 6 of them total, kind of the same idea, 2 of these phosphates. And then when we look at it, we're still conserving mass. We still have 2 phosphoruses. We still have 8 oxygens down here, 6 hydrogens total, and then +6, -6, balancing out. Calcium chloride going to split into those calcium and chloride ions. But since we get 2 chlorines for every calcium, and we've got 3 molecules total, we've got 3 calcium ions and 6 chlorides. And then again, pure solids, we're going to keep the same. The strong acid will separate into the hydrogen ion and the chloride ion. And now we've got that Cl ion on both sides. We've got the hydrogen ion on both sides. So we can remove those from the ionic equation to get the net ionic equation to show what's actually changing throughout this reaction. So in this case, the really only thing that's changing, because we're keeping the hydrogen dissolved, we're keeping that chloride dissolved. So the only thing that's changing is we're taking these calcium and phosphate ions and having them precipitate out of that solution to give us a solid product. All right, and then with the next one, we've got a stoichiometry example. So remember, with these, we always want to make sure we've got our balanced chemical equation. And in this case, it is balanced right away with coefficients of 1 because we've got 1 calcium, 1 carbon, 3 oxygens on each side. So we're told we've got 0.53 grams of carbon dioxide obtained from heating 1.31 grams of calcium carbonate. We want to determine what the percent yield is. So what we need to do is take this 1.31 grams of calcium carbonate and use this chemical reaction to determine if we actually reacted all 1.31 grams of this calcium carbonate according to the equation we see here. How much calcium dioxide could we possibly produce according to the conservation of mass? And then that'll represent our theoretical yield, kind of the best case scenario in terms of the efficiency of that reaction. So we can take our theoretical yield and compare it to the actual yield to determine the percent yield that we're interested in. So with the theoretical yield, that'll be kind of our 3-step process where we go from grams to moles. So this first one here, we're just dividing by molar mass to get the grams to cancel. And that would tell us how many moles of calcium carbonate we have in 1.31 grams. And then this 100.086 number, that's just from adding 1 calcium, 1 carbon, and 3 oxygens up on the periodic table. But now that we're in moles of calcium carbonate, we can put that unit on the bottom to cancel it. And since we're being asked about the carbon dioxide, that's why we'll have 1 mole of CO2 on top. And again, these ones here are just because that's the balanced chemical equation. So we've got coefficients of 1. So for every 1 mole of calcium carbonate we decompose, we'll get 1 calcium oxide, we'll get 1 carbon dioxide there. And now we have how many moles of carbon dioxide we could theoretically produce. But we're comparing it to grams, so we're going to go one step further, use the molar mass of carbon dioxide. And since this case, we're starting with moles on top, we've got moles on the bottom, grams on top. If we go through and actually do that calculation, paying attention to sig figs, because we've got 3 sig figs in the starting mass, so we want 3 sig figs in our theoretical yield, we could theoretically produce 0.576 grams of carbon dioxide. And again, that's kind of the best case scenario according to the law of conservation of mass in terms of this reaction being as efficient as possible. But if the scientist who's conducting this reaction only obtained 0.53 grams, we can determine the percent yield by comparing those. So what you got versus what you could have got, and then times 100 just to make it a percentage. So according to the 0.53 grams here, that would indicate a percent yield of 92%. And then I think this is the last one I have, but what is the limiting reactant when 1.5 grams of lithium and 1.5 grams of nitrogen are reacted together to form lithium nitride? And then with this equation, again, like I mentioned with the previous one, we always want to make sure we've got the balanced chemical equation. This one kind of gives you a little bit of a hint, unbalanced equation. So we've got 1 lithium on the left, 3 of them on the right, 2 nitrogens on the left, 1 of them on the right. So what I would do here is put a 2 in front of lithium nitride, balance out the nitrogens, but now we've got 6 lithiums here. So we can go to the reactant side and put a 6 in front of Li. And now with this question, there's multiple ways you could approach it. You could take 1.5 grams of lithium and, kind of similar to the previous one, determine the theoretical yield of lithium nitride. You could then do the same thing with 1.5 grams of nitrogen, figure out how much lithium nitride you could theoretically produce. And then whichever of those give you the smallest value would be our limiting reactant, because that's going to be the one that gets used up first. That's the one that could produce less. But what I'm going to show here is how we can compare these two substances to one another. And it's essentially the same process. It's just instead of relating a reactant with a product, we're going to relate a reactant with the other reactant. And you can do it in either way, but again, the key piece here is going to be to make sure we've got that balanced chemical equation. But if we start with 1.5 grams of lithium, we can go through the mole to mole, or mass to mole, mole to mole, mole to mass steps like we just saw. It's just in this case, we're looking at a different reaction, different substances. So we've got different molar masses in the first and the third step. We've got different coefficients in the second one. But if we go through and do this calculation, if we start with 1.50 grams of lithium and fully reacted it according to this reaction, we would need 1.01 grams of nitrogen. And if we think about it, this calculation on its own is enough to determine the limiting reactant and the excess reactant. Because if we want to react all 1.5 grams of this, we only need 1.01 grams of nitrogen. But we've got 1.5 grams of nitrogen. So we have plenty of the nitrogen here. So that would identify the nitrogen as the excess reactant because we have more of it than we need, making the lithium the limiting reactant. That's going to be the one that runs out first. Or if we look at this one, whoops, and I'm now realizing that I have the wrong substance at the end here. But if we look at the other reactant, we start with the 1.5 grams of nitrogen. We can determine the same thing. So you'll see our conversions are essentially reversed here, because now we're going from nitrogen to lithium rather than lithium to nitrogen. But we just have the molar mass in the first step to get the moles. We have the balanced coefficients from the reaction to go from moles of the first substance to moles of the second. And then we have the molar mass of that second substance to convert from moles to grams. So same process in both cases. It's just determining what are we starting with. But if we did start with 1.5 grams of nitrogen, we would need 2.23 grams of lithium. But again, we only have 1.5 grams. So since this is going to run out before we can actually react all of the 1.5 grams of nitrogen, that makes the nitrogen, again, the excess reactant, makes the lithium the limiting reactant. So there's multiple ways that you could approach it. But the reason I like this method is because if we wanted to also determine how much of the excess reactant is remaining, we already have that information provided because we're only going to need to use 1.01 grams of nitrogen. So if we have 1.5 grams of nitrogen, the amount that's going to be remaining is just the difference between those two. So we'd be left with just under 0.5 gram of nitrogen after we used up all of that lithium. But with it, I believe, yes. Okay, so this was the final one from the review. There is the answer key for the problem set posted in Canvas. And then on Monday, if you do have any questions, I have office hours in the afternoon, but also at the start of class, there will be a chance to kind of ask any of the final questions that you have before Tuesday's exam. So if there is a certain question on the problem set, certain question from any of the practice in Canvas, any of the practice in the textbook, let me know. We can pull that up in class and look at it too.